Concolic got his bachelor's and did his PhD at the University of Illinois at Urbana-Champaign. He worked in very many different areas within the domain of programming languages and made very many significant contributions in these areas. He worked in runtime verifications and monitoring of concurrent systems, statistical model checking, and the use of machine learning to verify infinite state machines. More recently, he has looked at the problem of using program analysis for automatic test case generation. And for this work, he received the ACM Distinguished Paper Award at the Symposium on the Foundations of Software Engineering last year. So, software testing covers a big fraction of software development cost, and because of that, this kind of work can have a big impact in industry. So having said that, I will let Concolic tell us about this work.
Thank you, Larry. So good afternoon, everyone. Today I'm going to talk about my research, primarily focusing on my work on scalable automated methods for software reliability. So let me first give you an outline of my talk. So I'll first motivate the problem, and after that I'll pick one specific topic of my research, which is dynamic program analysis and its application to testing sequential and content programs. And then after that, I'll give you some case studies which shows the applicability of my work. And after that, I'll give you the big picture, my research in other areas, and mention some future research directions. Okay. So why is software reliability important? Software is everywhere. It's pervading every aspect of our life. And software reliability is a grand challenge nowadays. In fact, a 2002 NIST report claims that software failures currently cost the US economy an estimated $60 billion. And if we can improve the software testing infrastructure, then we can save 1/3 of this cost. And it's not the case that we're not trying to improve the software reliability. In fact, if you go to the software industry, you'll find that 50 to 80% of the total development cost goes only into testing. So the developers and the industry is trying hard to develop reliable software. Unfortunately, the methods and the techniques are not good enough. So there are several approaches to address this problem of software reliability, such as safe programming languages and type systems, static program analysis, dynamic program analysis, which includes runtime monitoring, testing, and so on, formal methods and model checking and theorem proving, model-based software development and analysis, but each one has its limitation. For example, in case of static program analysis, you keep false positives, which overwhelms the developers. In case of testing, it's mostly done in ad hoc way, by manually translating the specification into test cases and then executing the program. In my research, I focused on this particular domain, which includes dynamic program analysis and involves runtime monitoring, testing, model checking, and some part of safe programming and model-based software development and analysis. And today I focus only on this testing part. So next I'm going to show you a new method of dynamic program analysis and its application to test sequential programs. Okay, so what is the goal behind testing? In testing a sequential program, we want to generate a set of test inputs so that whenever we execute the program on those inputs, we can catch bugs. Now for now, I'll only focus on generic bugs such as assertion violations, uncaught exceptions, data race deadlocks, etc. And later I'll talk about bugs related to the formal specification and functional properties. Now observe one thing. If we can generate a set of test cases or test inputs which enables the program to execute all reachable statements in the program, then we can catch any generic errors such as assertion violation or uncaught exception. Clearly we can do this if we can execute all the feasible execution paths of the program. So let me clarify this. Given a sequential program, we can see all the feasible execution paths of the program as a binary tree, where each internal node represents the execution of a conditional statement or an if-then-else statement. And each edge represents the execution of a sequence of non-conditional statements. Now observe one thing. There can be several inputs to a sequential program that would force the program along the same path. Our goal would be to generate a set of inputs, an optimal set of inputs, so that each path in this tree is explored exactly once. Obviously, if the tree is infinite in size, you cannot expect to explore the whole tree. In such case, we limit our bound with finite depth, or we can use heuristics like statistics or machine learning and so on. So here is an example of a computation tree. So this C program I use as a running example through the first part of my talk. And it has two inputs, x and y of type integers. And then it invokes this function double, which is defined here. It should not be confused with the double casting operator in C, which returns 2 times of its argument and assigns it to z. And there is conditional which checks z is equal to x. Then if x is greater than y plus 10, then there is an error. Now consider the execution of this program for all possible values of x and y. It forms this computation tree which has 3 execution paths exactly. Now our goal would be to generate values for x and y so that each path in this tree is explored exactly once. Now there are several existing approaches to address this problem. One such method is random testing. In random testing, you generate random values for the inputs and then you execute the program on these randomly generated inputs. Now, random testing is widely used in the industry and it proves quite successful in finding bugs, but it has its limitation. It gives very poor coverage. For example, consider this method test_me, which takes as an input x and which does this comparison. If x is equal to something, then there is an error. And if we generate random value for this input x, then the probability of hitting this error is extremely low, which is 1 by 32. And this probability becomes even worse if we have inputs which are complex data structures. Now, one way to address this problem is to perform symbolic analysis. In symbolic analysis, instead of using random values for the inputs, you initialize the inputs with symbolic values and then execute the program algebraically. And whenever you reach some conditional statement, you check whether either of the branches can be taken using a theorem prover. Now, symbolic analysis obviously will give better coverage because you are exhaustively searching the execution space, but it has its limitation. It cannot handle all the features of the real-world program. Consider this example, test_me, which takes as an input x, and which has this conditional x mod 10 times 4 is not equal to 17. Now, assuming that our theorem prover cannot reason about the theory of integers with the modulo operator, which is the case, then if we use symbolic analysis, at this point, we'll get stuck. We won't be able to reason whether error 1 is reachable or error 2 is reachable. And if it is a conservative theorem prover, it will, or it's a practical theorem prover, it will say both the errors are reachable. So we get false positive. Now, things become even worse if we have some function for which you don't have the code. And you have to make a comparison like this. So for this function f, we don't have the code, so we cannot do symbolic analysis. So at this point also we cannot decide and say whether error 1 is reachable or error 2 is reachable. To address these limitations, yes?
But the other approach cannot handle this case either.
Which
one? If you don't have the code for that, then you cannot use the other approach either, so none of them.
Yeah, none of them cannot address this problem. But you get stuck here, you cannot go down the tree. If it is a conditional statement, you just say, I don't know what to do at this point. So, to address these limitations, we combine symbolic analysis and random testing in a new method of program analysis called concolic execution. So, concolic execution, the term comes from C-O-N-C from concrete and OLIC from symbolic. We picked this name because it doesn't show up on Google and it's a bit controversial, so people will remember this name, I hope. So I started this work while I was doing internship at Bell Labs, and later I extended this work with pointers and data structures with concurrency and message passing systems and so on. So let me explain this method through the running example. So if we generate random values for x and y, the probability of hitting this error is extremely low. It's in fact 1 by 2 to the power 33. Instead, what we propose is to combine random execution or concrete execution with symbolic execution. So for that, we create two kinds of the state. One is the concrete state of the program, where we initialize the inputs with random values. In this case, x is initialized with 22 and y equal to 7, some random value. And then we also create another state which is the symbolic state of the program, and there we initialize the inputs with symbolic values which is x and y in this case, x0 and y0. And then we execute the program both symbolically and concretely simultaneously. So after the execution of this statement, which does interprocedural analysis, z becomes 14, which is the actual state of the program, and here in the symbolic state, z becomes 2 times y0. Now, whenever we execute some conditional statement, we generate a constant over the symbolic input values. In this case, it's 2y0 is not equal to x0. Now, observe one thing. Any assignment to x and y that satisfies this constraint would force the program along the same path. Our goal would be to generate a new set of inputs so that the program takes a different execution path. So what should we do for that? We take this constraint, we negate it and solve it to generate another set of input, which is x is equal to 2 and y equal to 1. Again, we repeat the process. We execute the program both concretely and symbolically. So z becomes here again 2y0, but now the constraint generated is 2y0 is equal to x0. And after the execution of this statement, the constraint is this: x0 is less than y0 plus 10. We repeat the process to generate a new set of input that forces the program along a different path. We negate one of the constraint and solve it to generate values x equal to 30 and y equal to 15. And now if we execute the program on this newly generated input, it actually hits the error. So in a way, what we tried to do, we had this computation tree, and we tried to explore this computation tree first by generating a random set of values for inputs and taking some path, and then picking one of the node, negating the constraint corresponding to that, generating a new set of input and taking another path, and we continued this process. So since we are exploring all the paths in this computation tree, we call this explicit path model checking rather than explicit state model checking. Now, you may question how the symbolic analysis is helping at all in the case of, in this testing method, how the symbolic testing is interacting with the concrete execution. So to illustrate that, let me change this function foo, the double function foo, which is written here. It returns some complex expression v times v modulo 50. And let us assume that we don't know how to solve constraints involving the modulo operator. Now, if we repeat the process of testing, if we do perform simultaneous concrete and symbolic execution, we generate this constraint which is y times y modulo 50 not equal to x. Now we have to solve this constraint. And we don't know how to solve the constraint with the modulo operator. So the question is, are we stuck? The same situation can arise if we have some function foo for which we don't have the code at all. Then we have to solve this constraint which is foo of y0 is equal to x. And we don't know how to solve it. So again the question is, are we stuck? No. Since the concrete state is a special case of the symbolic state, we can replace some of the symbolic values by concrete values. We are some, but we cannot catch all kind of bugs. And as a result, if we replace here y by 7, which is the concrete value for y, we get this simple constraint which is 49 is equal to x. And now if we solve it, we get the solution which is x equal to 49 and y equal to 7. And now if we execute the program on this newly generated input, we actually hit the error. So in a way what we did, we combined random testing and symbolic analysis, and we took the middle path between the two so that we can handle large complex programs. We can get high coverage, and we don't give any false positive. Because whenever we hit an error, we have a concrete input leading towards that bug. Now, I explained the concolic testing or concolic analysis using a very simple example so that it is accessible to a broader audience. Yes?
Yeah, I'm a little confused. So there's random testing, then there's concrete, concrete going through the concrete, and then there's symbolic.
Yes.
And it seems to me you started with something random, but after that you didn't do anything random subsequently.
Yeah, that's a good question. Actually, whenever we get some constraint that we cannot handle or some symbolic expression we cannot handle, we replace some of the symbolic values by concrete values. So we make approximation. And in that way, we may not get full coverage, and we may end up exploring some part of the tree. And when we go to the top of the tree, we again restart the process with random values. Moreover, at the time of solving the constraints, we also use random values to get new inputs. So that's how they together interact with each other. Yes.
So I was talking about this picture of a program as a tree. I mean,
Yes.
If I think about the control flow through a program that has like n different if then else things that are chained together, then I've got two to the end implicit paths through a structure that's actually very compact.
Yes.
So how does the example you described before, how would it adapt to that sort of thing where you couldn't possibly explore all the implicit paths?
Yeah, that's a good point you observed. In fact, if we have join points and then you have again diverge, again join, then we have to unfold it completely to get the tree. And in worst case, it may be exponential in the size of the program, and that is true. And we don't answer that question. But there are ideas like you can combine static analysis probably to enhance this dynamic analysis and probably combine things and get efficiency. So those are kind of future work that I'm looking at. Yes.
Sorry, one more question. In your programs, the error was this red word error.
Yes.
And if you ever get to that part of the execution, you instantly will find the word error. But some errors are more subtle. If you go through that branch and your value was 7, you didn't find it, but if the value was 8, you did. And it's not because there was a different branch of the execution.
Yes, that's a very good point. So you are referring that sometimes the bugs may be due to the state of the program, not due to the path of the program. And my next slide will address that problem. So some of the state properties we can always convert into path property by introducing some if-then-else statement. And for certain kind of properties like buffer overflow, this can be done automatically. So I'll get back to that. Now, so I explained the Concolic testing through a very simple example so that it is accessible to a broader audience, but things get really complex when you have pointers and data structures, when you have concurrency and message passing system. And I'll not go into the details how we handle pointers and data structures. That actually appears in our FSE, Foundations of Software Engineering paper, 2005, but I'll give you the summary. In case we have inputs which are pointers or object reference, then it can point to a memory graph or a complex data structure. And we symbolically represent them using something called a logical input map. And here is an example of a logical input map. This data structure is represented by this map. And then to track the constraints associated with the pointers, we use equality and disequality constraints over the symbolic pointer variables or object references. Of this form, P is not equal to null, P equal to null, P is not equal to Q, P equal to Q. And then to solve such pointer constraints, we observe one thing that we can sometimes decouple. Most of the times we can decouple the pointer constraints from the arithmetic constraints. This way we do approximation, but this way our constraint solving is very efficient. So what we do, we generate the equivalence class for each symbolic pointer, and then to solve the constraints, we either add a node or remove a node or make two pointers or references equal in the process of solving these pointer constraints. And this is an incremental way of solving. We also made the observation that in execution, we only negate one symbolic constraint and others remain almost the same. So our solution should be equal to our previous solution. And exploit this fact, and we implemented an incremental solver for this, which actually runs 100 to 1,000 times faster than a naive constraint solver. Now, this incremental solving really helps when you have pointers. If you see testing of a program having some pointer input, you will find that it gradually builds the data structure as it incrementally solves the constraints in each execution. Now, getting back to your answer, how can we translate this kind of state errors to path errors? This can be done automatically for some kind of errors, like divide by zero error or buffer overflow. We can simply put some if-then-else statement, which just checks whether I is less than not equal to 0, then it is fine, otherwise there is an error. In case of buffer, we check the bounds and so on. And then we can use our analysis simply. So in this way, we translated the state property into a path property. And we can now use our Concolic execution to find the bug. So this way we can catch like security bugs and other things.
what if you want to enforce some general precondition, postcondition kind of constraints? Could you do the same thing here?
Yes, so those are also code, and you have to just explore the paths in that precondition or postcondition. So that is orthogonal to our approach. And in fact, in our data structure unit testing, we actually have preconditions or invariants for the data structures, and we explore those things just to generate the inputs for the data structure library. And yes.
How would you include memory leak in this path model?
That's a good question. So it's not complete. We can translate it into path property, but what we do currently is to run it Valgrind. Whenever we execute one path, we run it to Valgrind and see whether there is any memory leak detected by Valgrind. So we combine it with.
But otherwise, it is not possible to express.
I don't know. I don't know the answer right now. So maybe. So I described this concolic testing for sequential program. Unfortunately, most of the real-world programs are concurrent programs, where several threads or methods execute concurrently and simultaneously communicating either through message passing or through shared memory. So next, I'll show how to extend this concolic execution or concolic analysis to handle concurrent programs. So the semantics of a concurrent program can be given in terms of a scheduler, where the scheduler at each point of execution picks non-deterministically one of the threads and executes its next statement. Now, testing concurrent programs is a notoriously hard task because for a given execution, the program can show different behavior depending on how you resolve the non-determinism associated with the scheduler. And if you perform manual testing of concurrent programs, you may not find a bug during testing, but it may show up in the field because of a different scheduling policy. So to test concurrent programs properly, you have to explore the program execution for all possible inputs and all possible schedules. But that is going to be a nearly difficult task to do because we get an exponential blow up. For example, if we consider this two-thread program where thread T1 first executes x equal to 100 and then this conditional, and T2 executes this conditional, then the computation tree for this combined program is this huge tree. And here we have nodes not only for conditional statements, we also have nodes for the scheduler choice or the thread switch. Now, if we just forget about one of the thread and just consider one thread, its computation tree is this one, which has only one internal node. So we get an exponential blow up. Now, to address this problem, there are several existing approaches. One such approach is partial order reduction. And they made the observation number of executions of a concurrent program are equivalent to each other with respect when we are worried about statement reachability or generic bugs. And they developed tools like Spin, are very soft based on these partial order reduction methods. But unfortunately, they do not consider complex data inputs. They assume that the input comes from a small finite domain. Say if it is an integer, it can only assume values 0, 1, 2, and 3. And then they try to explore the program behavior for each input by doing partial order reduction. So it does not scale for programs which have both inputs and concurrency. So another straightforward way would be to combine symbolic execution with partial order reduction. And that is done with the Java Pathfinder tool from NASA Ames. But it has its limitation. The symbolic execution has this limitation as I described before. But at the same time, for the partial order reduction, you have to determine the dependency relation among the various concurrent events. And for that, you have to do alias analysis. Since in symbolic execution, alias analysis or pointer analysis is always conservative, you may get a lot of dependency relation, and as a result, you will end up exploring a lot of redundant paths. So it does not really scale up. We observe that our concolic testing or concolic analysis is ideal for concurrent programs. Why? We can use the symbolic execution as before to generate test inputs. At the same time, we can use the concrete execution to exactly determine the dependency relation. So let me go into the key steps behind this concolic testing extended with rest detection and rest flipping. So the concurrent executions are often formalized in terms of the partial order relation. So we call an event in a concurrent system, in a concurrent execution, an event if it is an access to a memory location by a thread. It can be a lock, acquire, read, or write of the memory location. We say that two events are related by this partial order relation if they are events from different threads and if they are accessing the same memory location without synchronization, and one of them is write and the other can be read or write, or one of them is lock release and the other is lock acquire. Or if they are events from the same thread and one happens before the other. And then we take the transitive closure of this relation. Now note one thing, race conditions are exactly captured by this partial order relation, the way we defined it. Now, given this relation, partial order relation, here is the observation. If we can execute one linear order for each partial order, then we can catch any generic bug, or we can reach any reachable statement in the program. So, for testing what we have to do, we have to execute one execution from the equivalence class with respect to partial order. So, let me explain this through an example. So, here is an example of a partial order. Consider this two-thread program. T1 executes y equal to 1 and x equal to 1, and T2 executes x equal to 3, and if x is not equal to 3, then there is an error. Now, this is one particular execution of this concurrent program, where x is the shared variable, where we first execute T1 and then we execute the statements of T2. And this is the partial order corresponding to this execution, where we draw a line from this event to this event because they are in race, because they are both accessing the variable, shared variable x without any synchronization. Now, we have one partial order. What we want to do, we want to execute the program to get another partial order. We don't want to get a linear order of the same partial order. So for that, what should we do? We generate a new schedule where we execute the program, this event first, and then we postpone the execution of the thread T1 here. And then we continue the remaining of the execution. As a result, what we did, we had this relation between these two events, we flipped them or reordered them. So in a way, we reordered the rest condition between the two events by postponing one of the thread. And as a result, we actually hit the error. So in summary, in this new method of extending concolic testing with rest detection and rest flipping, we try to reorder the rest events in a systematic way along with generation of new data inputs. And for this algorithm, I'm not going to the details, we have to actually make sure that we do not reorder two events that we have already flipped. So we have to take care of those things, and we do by maintaining some kind of sets like postpone set and slip set. And for this algorithm, we prove that the rest flipping algorithm explores one linear order for each partial order. Now for the rest detection, we use the concrete execution, and there we use one of our earlier results called dynamic vector clock algorithm. And we developed in 2003 in the context of runtime monitoring, but later we found that it can also be used in rest detection, exact rest detection in case of concolic execution. And this algorithm respects the fact that two reads can be permuted, they are not dependent. But write is always dependent with a read or another write. And for this algorithm, we prove that if any two events are related by this partial order relation, then the vector clock of one event is component-wise less than or equal to the vector clock of the other event. And it is worth mentioning that we took this lemma as our goal and we derived this algorithm mathematically. So, if we consider this combination of concolic testing with rest detection and rest flipping, we end up exploring this small part of the tree. And in fact, our case studies will show that it is quite effective and efficient for real programs. And finally, we prove the correctness theorem, which says that we are always sound. Sound means whenever we detect a bug, we have a concrete set of inputs and a concrete schedule that acts as an evidence for that bug. So we can replay it using a debugger. We are complete in a limited sense. If our algorithm terminates, and if we are not doing any approximation, and if we can solve any constraint that we have generated, then we say that we can hit all visible statements in the program. So good. So far I described a new method of dynamic program analysis which can be used to find bugs, generic bugs in concurrent programs like assertion violations or data race, deadlock, etc. So this method you can see as an effective way of exploring all the feasible execution paths of a program. And obviously it is directly applicable to testing. Unfortunately, bugs in the real world are not only generic, but they can be due to some formal or functional reasons. There may be a formal specification. So I will not go into the controversy whether we should have a formal specification or not, whether it is complete or correct or not. Just assume that we have some formal specification of the program and you want to check the correctness of the program against this formal specification. Now I'll show an example which will illustrate that our method is not complete when we have a temporal formal specification. So we need to modify this method. So consider this two-threaded program. T1 executes x equal to 3 and T2 executes y equal to 2. Now, our method that I described earlier will explore this one execution of the program, which is you first execute T1 and then you execute T2, and it will stop, because this is the only partial order in this program. So we are fine. We have reached all the reachable statements in this program. But consider the fact that we have a formal specification which is of this form. Always x is greater than equal to y. Now this particular execution of the program satisfies this specification. In fact, always x is greater than or equal to y. Unfortunately, there is another linear order of the same partial order which actually violates this property. At this point, x is equal to 0 and y equal to 2, where the property gets violated. But it's the linear order of the same partial order, and we will not explore it using our previous method. So our question is, do we have to explore the whole computation tree? The answer is unfortunately yes, if we have a temporal specification. But we have good news. We developed a new method called predictive analysis, which can explore all the linear orders of a partial order efficiently without re-execution, without generating schedules for each of them. And this we call predictive analysis. So let me give you the intuitive idea behind predictive analysis using a simple example. Yes.
Sorry, I have one question. So, unfortunately, yes means there's a proof that you have to, or that it's hard. I was wondering what unfortunately yes means.
Well, we don't have a proof, but I showed you an example. Means I don't know whether we have to explore all the linear orders, but we have to explore at least 2 or 3 linear orders for each partial order to find this kind of bugs, or maybe all the linear orders of a partial order to find such kind of bugs. So the answer is exploring only one linear order for a partial order is not sufficient. Suppose a cyclist is trying to cross the road because the walk sign is on. At the same time, because there is some problem in the traffic system, the green signal is also on and a car is moving on the road. Now the cyclist misses the collision with the car, fortunately. Now from this scenario, can you say that something bad happened or something is wrong with the traffic system? If we are doing testing, we'll say no, because nothing bad happened. We didn't observe any accident. But observe one thing, the crossing of the road by the cyclist and the movement of the car on the road are causally unrelated. So we can always generate another new scenario where we reorder these two events and make the car hit the cyclist. So in this way, from a successful scenario, we have predicted a scenario where the property gets violated. Actually, the car hits the cyclist. And this is the key idea behind predictive analysis. We take into account the causality information associated with the concurrent execution and try to generate effectively other linear orders corresponding to a partial order in the form of a mathematical structure called computational lattice, which you can find in distributed systems, and then check the formal specification against this lattice. So I'll not go into the details of this method. So essentially what we do, we take the event trace, which is annotated with the dynamic vector clock algorithm that we described before, and annotated with the partial state update. From that, we construct this computational lattice, which you can find in the distributed algorithm literature. Each path in this computational lattice represents a linear order which is equivalent to this linear order, or which are the linearization of the same partial order. Now, to check a temporal formal specification or safety property against this lattice, we have to enumerate all the paths in this lattice and check if each of the paths satisfies the formal specification or not. But if we implement this naive algorithm of enumerating all the paths in this lattice, it will have a time complexity which is linear in the size of the past time linear temporal logic formula and exponential in the size of the computational lattice. We proposed a new algorithm based on dynamic programming which shows that the lattice can be explored in time which is linear in the size of the formula and linear in the size of the lattice. And finally we prove this theorem, given a past time linear temporal logic formula, if we find a violation using this algorithm, then there exists at least one linear order that violates this property. It may be the case that the original execution may not violate the property. So in a way, from a successful execution, we have predicted another execution that violates the property. So if we combine everything, the Concolic testing, race detection and race splitting and predictive analysis, we get an automated and systematic method for exploring all the paths of a concurrent program and check it against a formal specification. And based on this method, so these are like I showed you some theoretical results and lemmas. So you may now question how effective is this method. So based on this method, we implemented two tools. One for testing C programs, which we call Qt, Concolic Unit Testing Engine, and other for Java programs, which we call JQt. And both the tools are quite robust. They're available from my website for download, and they're not prototypes. So developers and researchers are using them. So I'll now show you some of the case studies that I have done on using these tools. We took the SGlib library for C data structures, which is a popular data structure library and widely used, and it is used in one of the commercial tools called Xrefactory for refactoring C and C++. And we took this data structure library just to evaluate our tool, and we didn't expect to find any bug because it's widely used. But surprisingly, we discovered two bugs in this library. One such bug is the suspension fault, which occurs when you try to concatenate a non-zero length list with a zero length list, and other is an infinite loop in the hash table. And we found both the bugs within less than 1 second. And it is worth mentioning that in case of hash table, we have some complex hash function which is not friendly towards symbolic execution. But since we are doing this combination of symbolic execution and concrete execution, we are able to go deep inside the tree and find this bug. So here is the statistics for this testing. In most of the cases, you will find that we got branch coverage which is greater than 96%, and we can test the program within less than 5 seconds of running time. In case of hash table, since we have this complex hash function, we were not able to get a very good coverage, which is 85%. And in case of red-black tree, we found that there are a lot of assertions in the program that was written by the programmer just to check the correctness of the implementation. And these assertions can be treated as branches, and these branches can never be violated. So we got a very less coverage in that case, which is 71%. Ideally, we should have done code coverage, but we didn't do that. And for red flag tree, the running time is quite high, it's 45 minutes, because it has a lot of code and it's complex data structure. We also took the Java JDK 1.4 library, the java.util package, And there are a number of collection classes are claimed as thread set. That is, if you execute multiple methods of multiple objects from this class by different threads, then they are serializable, as if they are executed by a single thread. Now, we took this library to evaluate our algorithm for concurrency. We didn't again expect to find bug, but surprisingly we discovered previously undocumented problems in this library, which includes like data race, infinite loop, uncaught exceptions, and deadlocks. And one such scenario is this one. If we have two linked lists which are synchronized, and if we execute L1.clear in one thread and L2.containSort in the other thread, then we actually can get a schedule which leads it into an infinite loop. And here is the statistics. Here we are not concerned about branch coverage because we tried to test it against the thread safety property. So we restricted up the number of paths to 20,000. But the number of errors are quite high. But I have to mention that these errors, although the number of errors is high, they are only due to a couple of problematic design patterns used in implementing this library. And they can be fixed easily. We also compared with two existing state-of-the-art tools. One is the very soft tool, the C model checker from Bell Labs. And we took the C implementation of the Needham-Schroeder protocol, security protocol, and the TMN protocol. And in both the implementation, we found the known attack within less than 15 seconds. In comparison, Verisov took 8 hours to find the same attack in the Needham-Schroeder protocol. And when they used heuristics with manual guidance, they found the attack in 55 minutes. So we are far better than this model checker, Verisov model checker. And the reason is we perform this concolic execution, so we can also generate inputs dynamically. The other thing we also compared with the Java Path Explorer tool developed at NASA Ames, and we took all of their case studies and performed comparison. One such case study is the DOS real-time operating system, and there we found a subtle time partitioning error in less than 1 minute. Our tool JQ found this bug. In comparison, Java Pathfinder actually ran out of memory when they tried to model check the actual program. So they had to create a manual abstraction, and then they discovered the bug in 11 minutes. Now, I thought that part of my tool, Q, is written in C. So I thought I should really test my tool using the tool itself. And before testing, I was quite confident that I'm a good programmer, so there should not be any bug. We can find bugs, but we cannot have any bug. But my misconception was broken when I found several segmentation faults and memory leaks in the code itself. And since then, I always test Q using Qt itself before I check in. Now, these methods and tools have done some impact. This tool Qt and JQt are available for public download, and many researchers and developers are using it. And I always get requests for new features and bugs and other things, and they also thank me for finding this and that bug and so on. And there has been some commercial interest in this tool. Microsoft showed a lot of interest in actually in this technology, and they want to implement it in their product group. A testing company actually showed interest in licensing our technology because we filed 2 patents on this. And one of our local venture capitalists, Illinois Ventures, actually showed interest in starting a company based on this technology. So far I described a new method of dynamic program analysis and showed its application to testing. So now I'll briefly describe my research in other areas and give some future research directions and give you the big picture. So, as I mentioned, my focus is on dynamic program analysis of concurrent and distributed programs. And today I only describe testing, and the remaining things are this. So today I explained concolic testing, race splitting, race detection and flipping, and predictive monitoring. So this part of the diagram I explained so far. But testing cannot catch all kinds of bugs because it's incomplete. So there one can use one of my methods called runtime monitoring or runtime verification. So the idea there is, given a formal specification, we synthesize some kind of small state machine or monitors and insert them inside the program through instrumentation. So that whenever the program is executed, these monitors can check the satisfiability of this specification against the current execution. And this we call runtime monitoring, and one of the tools is Eagle that we developed at NASA Ames, which is part of the Java Path Explorer tool now. Now, monitoring becomes interesting when you have distributed systems, because in distributed systems you have to monitor execution, then you have to construct the global consistent state of the program. And for that, you have to get messages for every state update, and it must be collected by central monitor. And then you have to check it against the specification, and this becomes a huge overhead. So what we proposed combining epistemic logic with temporal logic, and we showed that such a logic can express interesting properties of distributed systems, and it can be monitored efficiently and effectively without any message overhead. And in content systems, I already described how we use the monitoring approach to do predictive analysis. Now, this kind of technology or methods can be used directly to programs. Like you take the C program or Java program and you can directly apply these methods to them. But I'm also interested in methods that are applied to the design phase of the development, software development, like modeling and model checking and verification. And half of my research work goes into this part, which includes probabilistic programming. So we extended derived theories with probabilities, and we call it probabilistic derived theories. So this kind of programming language is very suitable in programming network protocols and sensor network, where you want to replace some of the non-determinism by probabilities. Now, once we have a probabilistic program or a probabilistic specification, we may also want to check the correctness of such a specification against a probabilistic property. So we develop statistical model checking for that. So in this probabilistic properties can be like quality of service properties or something like that. Like if I send a message, then the probability that the message will be received at the receiver within say 100 units of time is greater than 0.99. So this kind of properties we can model check against the probabilistic programs. In a collaborative work, I also applied computational machine learning to verify infinite state systems. So in general, verifying infinite state systems is a hard task. Mostly the automated techniques don't work. And people use theorem proving to prove the correctness, reachability of such infinite state programs. So people made the observation that the reachable state space of such infinite state protocols or programs or models are sometimes regular. They form a regular state if the state is encoded properly. So we applied computational machine learning to infer this reachable state space and then check against the safety property. And we in fact ended up proving the reachability property of several models that were not possible before. So there are some common things in my research. All of them are dynamic. I execute the program and then analyze them. They are scalable. I always try to give up completeness by doing approximation so that things become scalable. They are automated. I try to focus on content and distributed programs in general, and brought in ideas from other disciplines like statistics, randomized algorithms, operations research, formal methods, and so on. And I not only developed the theory for each of these things, but I also built tools which are robust and which can be applied to real-world programs and software. In particular, I developed Dart, Qt, and JQt for Concolic testing, Eagle, which is now part of Java Path Explorer tool at NASA Ames, and so on. And we did a lot of case studies. Some of the case studies I already described. But we also used our runtime monitoring tool, Eagle, to find bugs in the Mars rover software at NASA Ames, which is like 35,000 lines of C++ code. We also tested the OSIP protocol at Bell Labs, which is 50,000 lines of C code, and we found several safety and security vulnerabilities. Also used statistical model checking to prove the correctness of a denial of service resistant TCP/IP protocol that was developed. So that is an overview of the research that I have done. So here is the research. So I'll conclude my talk with some future research directions. So software is everywhere, and software reliability is a big challenge. And in my research, I tried to develop methods based on dynamic program analysis which address this problem of software reliability either by doing testing or verification or model checking or runtime monitoring. But I believe we have only scratched the surface of this problem, and there are lots of things that needs to be done, and it just shows the light towards that direction. So in long term, I would like to work on several ideas. One is to extend this dynamic analysis methods to other domains like hardware, embedded systems, and event-based systems. I'd also like to make software self-monitoring and self-healing so that whenever it can check at runtime whether something is going wrong or not, and it can take necessary actions. My work on statistical model checking also shows that we can expect to give some measurable confidence in the quality of the software. So this is a big challenge, and I'd like to give some measurable confidence in general for software systems. In the near term, I have some ideas that I want to work on. For example, I want to combine static and dynamic analysis so that not only we can find bugs, but we can prove correctness of some part of the program or some part of the computation tree. So this is one thing I'm working on. I'd also like to scale these things for evolving software or evolving programs. So programs, you always change a little bit and get another version of the program. Now we have done some testing of or analysis of one version of the program. Now if you take another version, you have to redo the whole work. The answer is no. You can utilize your previous analysis and use it for the changed program. So I would like to work on this problem also. And finally, to apply these dynamic analysis methods to Linux kernel and big software systems, I'm also interested in decidability results of concurrent systems and coming up with new safe programming paradigms for concurrent systems. And in the process, I would like to combine techniques from formal methods, software testing, machine learning, runtime monitoring, operations research, and so on. So there are a lot of related work in this area. So here is a listing, so I will not go into the details. And finally, in my research, I collaborate with several people, both from academia and industry, and I would like to thank them. And finally, here is my conclusion. Thank you.
Any questions?
Yes.
So recently, my boss, I think he doesn't like me, just gave me 3 million lines of C++ code and said to clean it up. Do I stand a chance with your tool, or is it just not going to be able to handle that kind of complexity? This is a program when you start it up, it runs for about 9 days. So I'm just wondering.
Yeah, that's a very good problem. So currently we applied this dynamic analysis to unit testing and to small size systems, but not to 3 million lines of code. Because to scale this testing method to very large programs, you have to generate inputs for each run, and that may not be possible. But there are ideas. So we are working on one idea where we actually execute the program up to certain depth using random testing, and then around some part, which I'm concerned about, I start concolic testing and try to find bugs. And this is one way to scale things. Other ideas is to combine with static analysis. Like static analysis may give some results which you can use to prune the search space for dynamic analysis. So these are kind of ideas that can help in scaling our problem to Linux kernel or some very large software. So that is one of my future research ideas.
I'm a bit puzzled by your timing results, because you say concolic testing found a bug in so many seconds, whereas some other tool took much longer.
Yes.
Given the fact that you're relying on random inputs, right, it would seem like you should get some sort of a distribution for the time it takes, because presumably some inputs are not very useful for detecting that particular bug, and then you try with a different random input, right?
Well, that's a good point. But we also generate inputs based on the white box analysis of the program. So we start, the initial thing is with random values. But at the same time, we also generate values based on the dynamic analysis of the program, and that helps direct the program along the bug. So that is the place where we win. And in the comparison, actually, the tool Haysoft, it works only for concurrent programs. For the inputs, it just assumes a finite space. So if it has to enumerate all the inputs, it basically runs out of time because it cannot do. Because we generate these inputs by doing the dynamic analysis, we are able to restrict the amount of inputs that we have to generate to a small number. And so we run faster than that tool.
No, I understand why you run faster.
Mm-hmm.
I'm just surprised that you don't have a distribution there, because it seems like some random inputs perhaps will not be helpful for finding that bug, and so you have to try again, right?
Yeah, that's a good point. That's a good point. We don't know the distribution of the inputs. And we just do a uniform sampling from the input space. But it would be nice if someone can come up with the distribution over the input space. And it can be done either through by looking at the behavior of the program in the field or something like that. But we don't have the answer right now.
Let me try pushing on that one more time. Are you saying that you would find a bug in 9 seconds no matter what? Or is it possible sometimes it will take you longer and sometimes less?
Sometimes it will take longer. So, so note one thing, but we'll perform better than any other tool. Now, note one thing, we are doing depth first search. So we may end up, if we have a very large program, we may end up searching one part of the tree and get stuck at there. But the bug may be on this side of the tree, and we may not even reach it. So there we have ideas like how to use probabilistic sampling of the branches so that we can reach the bugs quickly or uniformly at random. So, or to use machine learning to prune the search space. So these are like future agenda, research agenda, which can help to reach the bugs quickly. And I don't have an answer right now.
There's another question, I guess, it runs to the future research, but we run a lot of Monte Carlo simulations in my lab. They begin with a random number seed. That's their only input. All the branches are randomly generated. How do you deal with that? Analyze the bug.
All the branches are engagement.
Well, you generate random values based on a random number seed for,
Yes.
and then you start doing a simulation. In our case, of a particle physics detector. It's very hard to find bugs if you don't have any inputs. Using the method you described before, is there a model that you can come up with in a probabilistic line that might?
Yeah, so that's a very good point. In case of if you are doing simulation, so that was the problem we addressed in statistical modeling. You may have many simulated traces. Now, can you use these things to give some guarantee, quantitative guarantee in the correctness of the program? And exactly that's what we address in this work on statistical model change.
Other questions? Let's thank our speaker.
Remember I said that whether you're using fast or slow Paxos is determined by the ballot number. So switching from one to the other is simply a matter of the leader deciding to say, okay, I'm going to send a 1A message for a new ballot number. It's the same algorithm.
Thanks very much, Leslie.